All right, the last two topics. One is I just want to take a quick look at something we looked at before, which is that heat is the movement of molecules. We talked about this last week. I really want to bring up an example though. So the thermal energy in a molecule, and this one we got a chart here for oxygen O2. Thermal energy in a molecule gives us its average velocity, and this is a different kind of average than you're accustomed to. This is a root mean square velocity, which is really more of a question is where is the average energy, not so much the average velocity, right? So your root mean square velocity gives you the average energy. And it involves this constant here called the Boltzmann constant, not to be confused with heat conductivity, completely different thing, right? And the temperature in this equation has to be in Kelvin. The mass has to be in kilograms to work all this out. So I wanted to look at a quick example to give you an idea of how fast are the molecules in the air that you're breathing right now moving around. All right. So let's take a look at oxygen at room temperature. Room temperature about 22 degrees C. You may keep your house a little bit colder, a little bit warmer than that, but 22 degrees C is 295 Kelvin. The mass of an oxygen molecule, O2, is about 5.3 times 10 to the minus 26 kilograms. And then there's the Boltzmann constant for this, 1.38 times 10 to the minus 23 joules per Kelvin. If we stick all of that into the equation, 3 times K times the temperature divided by the mass, and it's going to end up being in meters per second, we get that these oxygen molecules in the room are zipping along at 480 meters per second. 480 meters per second. That's over 1,000 miles per hour. So they're really zipping along pretty fast. This is why it's so hard to make liquid oxygen, because you have to cool them down a lot to get them to where they'll slow down enough to become a liquid. The same with nitrogen, and then some of the lighter molecules like helium, hydrogen, even harder. You have to really get them cold before they slow down enough to become liquid. There's another aspect to all this movement of molecules. It's called blackbody radiation. Blackbody radiation is really just a matter of, because the molecules in anything that has any temperature at all other than absolute zero are moving around, because those molecules are moving around, they give off some radiation. And radiation in terms of basically photons, light that you can see, light that you can't see. We typically think of it in terms of the infrared and the visible. So if you look at this flame or these two flames here, you can see here the bluer flame, the blue parts are actually hotter than the reddish orange parts. The blue parts are hotter because blue corresponds to higher temperatures, right? And the red parts are cooler because they correspond to lower temperatures. But everything emits blackbody radiation. In fact, early in the presentations here, there was this thermal image of a person's face, and this thermal image is using the blackbody radiation coming off of the person. You can find images of homes that show you where heat is leaking out, where it's not well insulated. That's all because of blackbody radiation. Blackbody radiation is how we do infrared photography. It's how we do all kinds of things with imaging. And in this is something called the Stefan Boltzmann constant. But we're not going to really worry about, there's the area of the object, there's a quantity called its emissivity, which is really how much does it reflect or absorb light, and then the Stefan Boltzmann constant. The key thing here is this goes as temperature to the fourth, and this has to be Kelvin, right? When you're talking about it, it has to be Kelvin. And we look at the net flow of heat out or into an object due to blackbody radiation, we end up with this equation where your black body, or your black body. We call it black body because this is radiation that has nothing to do with whether or not the object has any color or any light coming out of it that it's emitting. This only has to do with its temperature. So because it's temperature to the fourth, the net heat flowing to or from an object is its surface area times its emissivity times Stefan Boltzmann constant times temperature to the fourth of the object minus temperature to the fourth of the environment. All right, so the object can be radiating more energy out into the environment than it's getting, or it can be absorbing more energy from the environment than it's giving out. All of those can be true. If you take astronomy or play with telescopes a lot, you have to worry about this because you take a telescope that's sitting at 295 degrees Kelvin and you point it out at space, which is sitting at 2 degrees Kelvin, and you discover that that your telescope will cool off just due to black body radiation. Okay, that's the last bit on radiation. This is a different kind of radiation that's important when we're doing observations of different kinds, and hopefully you guys will actually get a good grasp of the problems and the concepts, and I will talk to you again later.